Hello and welcome to Database 1, COP4708, 4708, and Dr. Ron Nicklin. This is Module 6. We've been working on ERD, and now we're going to look at how we're going to actually take those ERDs and turn them into a design. So, it's really not a very difficult type of thing to do. We've got entities and attributes, and really what we're really doing there is we're going to replace them with tables and columns, which look almost the same. And we have identifiers. We're going to replace those identifiers with keys. That's what they are in database terms. And first things first, primary keys. Then the next thing is relationships, and that'll be, those relationships will be foreign keys. And then we have logic, the logic for the cardinality. A lot of that logic will be kind of automated, but some of that logic will require you to do special things. What we're going to do is say, usually if you need too much logic, it's not a good idea to do it anyway. But we're going to look at that with some examples. So what you do is, once you've got your entity relationship all laid out and how you do it, right now the process is to create tables for each entity. Now a lot of times in the design process, especially if you know the database well and you know that the ERD is really going to match the table structure, a lot of times people just actually start with the table structure. but we're going through the formal process now, so what we want to really do is look at how we're going to do this. So an example we've had from all the old lectures is that good old employee, and what we're going to do here is we had an employee number that went with that employee entity. So now we have an employee table, and we're going to set a primary key, and the primary key is unique and it's required. You got to have it. In this case, that primary key is a surrogate key, but I actually truly prefer that almost every table have a surrogate key, some sort of ID or some sort of number that's generated by the database to ensure that each of the records is unique. So if you look at the way that the diagramming tools work, when you're making entities, they have a little shading behind them. If you're making a table, they don't. So and the primary keys get little keys next to them. Actually, in many of the tools, so do the foreign keys. And sometimes the foreign keys are put up here at the top. Sometimes the foreign keys in some of the tools are actually down here in the with the other attributes. Okay. The thing about the surrogate key is it's used for the database to keep track of stuff. It usually doesn't have any real meaning to the user. The employee number is just something that's used internally by the database to keep track of the records, and everything is functionally dependent upon. In that table is functionally dependent upon that primary key. So, candidate keys are keys that could be used as an identifier. They do need to be unique, and sometimes it's a good idea to just annotate that those are candidate keys. Actually, a lot of times it's a good idea just to indicate that those are unique, that they're unique records too. And you have that ability in good old SQL, which you haven't learned yet, to do that. So when we're using tools like ERWin, what you're going to see is you have employee number here, which is the primary key for employee, but you've also got these other keys, things that could be a key, like the email should be unique to the employee. You shouldn't have multiple people with one email, and so it becomes a candidate key. But reality is that it is not the primary key. You've also got other ones that can be used as primary key, like the customer, again, candidate key being the email. You could also have a combination of, let's say, name, city, and I actually don't think name and city would be a good candidate key together. But the way this is marked as 0.1, 0.2, reality, I think this one here would probably maybe name, city, and phone as 3, but you really don't want to have 3 keys. You're good having this good old surrogate key of customer number is really the way to deal with this. And I will say it is the best way to deal with this. Now, we haven't learned SQL yet. SQL, SQL, that's what we call it, standard query, structured query language. But we have the ability to set the null status of specific attributes. This will be, actually in the case of the table, would be columns, and whether they're allowed to be null or not null. And this is something that you do. You actually want to specify whether this can be null, whether it can be null or not null. So like in the case of the employee number, since it's the primary key, can definitely not be null. That's important that it's not null. And some of the SQL processors with the databases will actually, when you set it to be the primary key, will set the null property to be not null. Also, you really want to have the name. That's kind of one of the biggest identifiers of that. So you would set that not null. This is logic. This is business logic. An employee number with a no employee name would kind of be a very difficult table to use for end users. So you're going to be making those decisions as you're building the tables of every single column or every single field, or if you're looking at ERDs, every single attribute, whether it can be null, in other words, no value there, that's what null means, no value, or not null. It must have a value. And that doesn't mean a blank value. I mean, it doesn't mean a value of like 0 or a value of a blank string, like a string with no characters. Null is its own thing. It means nothing has been entered there. All right, so when you build these tables and you build these columns and you need to tell it what type of data types to use. I typically, varchar is my favorite data type. Char actually is okay. There's a lot of personal feeling about how you put these data types in, but you need to tell the table what the field is going to be. So especially in the case of like date fields or date columns, I mean, a string is a string that it says, January 1st, 1975. That is not, it's a date as far as you can read it, but not necessarily the computer. You can convert it to a date, but dates are dates. They're specifically dates, and there's actually date time too. So you can get date and time. If you want to, I've given you the references that I in the Falcon Online. You've got references to where I think is the best place to go as a reference for all the data types. I am going to just quickly move through this big old list of a lot of the different types of Oracle data types. And by the way, those are not all of them. Now, I will go to one thing that I will say here. When you specify a varchar, you typically specify how big it can be because the database reserves space. I tend to use nvarchar max a lot. That's a Microsoft one, nvarchar max, which basically says it can go to as max as what it can. Is it good practice? Not necessarily, but in the case where I don't know how big it's going to get, I just go, let's just make it max because I don't know how big it can possibly get. And but the nvarchars actually have a better way of storage so that it doesn't eat up all of your memory or all of your database storage by making a bunch of things have nvarchar max. So another thing that you can do for every single column, every single field, is you can give it default values. Okay, that is a possibility. And sometimes the default values can be conditional. The most important of those default values is likely going to be your surrogate key, because you can identify the surrogate key to be an identity, I-D-E-N-T-I-T-Y. That is a keyword in the database. And what it will do is every time you create a new row in that table, it'll increment the maximum of those by 1 and assign that value. So you always get a value in that primary key space as long as it's numeric integer. Okay. But that is commonly what you're going to do. We're going to see this as we get into database design. There's some really good practices that you can put together to do it the right way. And you've also got different ways to make constraints on the value. So you can say that a column can only have a value of this specific set, or it can only be between 0 and 10, a range, or it might be dependent upon values that are in the same table, or it might be dependent upon values that are in other tables. Those are all things that you can do. And why would you set up constraints like this? Well, to keep the data from getting dirty, to keep it tight. Tight data that stays within the ranges of what it should be, within the constraints, is clean data. And clean data is a lot easier to use than dirty data. And dirty data usually has all sorts of values that fall outside the constraints, and sometimes it might have, well, you shouldn't have nulls where you can't have nulls, but dirty data is often a mess. And don't worry, you'll get your chance to play with dirty data and have to figure out ways to clean it up. So you should have at least some level of normalization of your tables, because you're not going to have one table, you're going to have many tables. And remember, we talked about normalization being this process where you avoid having duplicate data, which you could easily design tables that have that. And a typical normalization level is good old voice cod or BCNF or 4NF is the one that's typically used as a good practice. Does that mean that a database that doesn't have everything in BCNF is a bad database? Absolutely not. Okay, but when you're first designing it, a lot of times you'll start at BCNF, and as you build business rules into your database, you start realizing where you might want to break that level of normalization. So let's talk about one-to-one relationships. In other words, you got one on one table will always match something on the other table. And what you're going to do is you're going to make a foreign key to one table that points to the other one with a one-to-one relationship. And it looks kind of like this. You've got, let's say, in the case of a club member and a locker, the club member has one locker. Is it logical to put that locker into the club member stuff? Well, it might be that you put the locker number with the club member, and then over here on the other side, you've got a table that contains specific information about the lockers. And logically, in my head, the club member having the locker number in their table, and then the locker being purely information about the locker itself makes logical sense. But that's in my head. It may make sense that when you're looking at a locker, the thing that you really want to know is who that locker belongs to. In that case, the foreign key would be over in the locker table. Okay, again, the logic in this case is how exactly do you plan on using these tables will make a difference. So in the case of a one-to-one, I mean, they are specifically parent-child. In the one-to-many, it makes a lot of sense that the parent is the one and the child is the many. But in a one-to-one relationship, it doesn't, I mean, there's no way of saying, oh, well, this is the more logical parent or the more logical child, other than the business logic, but we still use that concept of parent-child. At least the terminology many times. That who has the foreign key? Well, the foreign key is sitting there with the child. So, strong entity relationships versus, we're not looking at strong versus weak. Remember, in the case of the strong relationship, the other table can exist without the other table. The tables don't need to, rely on each other. So you can see in this case here a 1 to n strong entity relationship, but oftentimes it's a good idea to place the key of the parent in the child so that it's easy to go back to, so the department does actually have a reference back to the company name. The department doesn't have to necessarily keep track of what company it belongs to, But many times it does help you when you want to, suppose you want to make a report and you want to get the company name and city and country, or company name and city onto the report for a department. That link back from the department to the company makes sense. And that is a business use case. The fact that you may want to do that. In the first situation that you see here, where you don't have that company name in there, it's a little bit more challenging to figure that out. So, what about when you've got one to or many to many? So in the case of this one, a company can supply many parts, and a part can be supplied by many companies. They're a many-to-many relationship. How do you deal with that in the table design? Well, hopefully you've already kind of thought about this a little bit, because what you need to do is you need a table that describes the relationship. What I mean is you need a separate table to do that, right? So we can call it an intersection table. Oftentimes it's called a relational table. A lot of times it has the name of both of the tables that it's got relationships with in the name of the table. So like the company and part table, where they relate together, might be the company part table. Or in this case, we're using the term company part int, or intersection. And what do you do there? Well, you put a foreign key in that intersection table to the tables that it relates to. So a company part has a link to the company name, and it has a link to the part number, and both of those are foreign keys in the company part int, but they're primary keys in the original table. By the way, that is how it has to be done. You cannot create a foreign key, at least in almost all databases, that doesn't point back to the primary key of the table that it's pointing to. Makes sense? And now we actually have the relationship between the company and the part, and it's a many-to-many. Companies can have many parts, and parts can have many companies. So you can see that you've got this ability to relate many to many with that association. And the intersection table, the relational table, can also contain other information that helps define the relationship. So the real thing that you're doing this design on is the cardinality, that many-to-many relationship that you have there. So we'll call this an association. Okay. Now, the intersection table contains the two foreign keys, which are the primary keys of what they are pointing at. You can put them as a composite primary key, and they can still be foreign keys. Okay. Doesn't mean you have to do it that way. I typically prefer to have the relational table contain a single surrogate key, that is the primary key, and the foreign keys are not composite primary keys, and they're not primary keys in any way, shape, or form. Those are two different types of design. And the reality is, which one do you want to do? You want to do that makes the business processes for your database the easiest. So we'll just show it right here. Notice in this case that I've got part and company, and part number and company name are both up in the primary key field, and they're foreign keys to other pieces. And in the quotation itself, we've got the price. So part number and company name being a composite primary key, and foreign keys linking back to the part and the company. Oops, I'll go down here. So here's some just examples of how you would take something in between the ERD and the table design. Note, it's not that terribly difficult. Just note that in this case, you've actually got a foreign key. And in the case of the phone contact, that foreign key is also part. of the primary key. It's a composite primary key in this case. Okay, same thing here. You can kind of see that foreign key, composite key piece. Okay, this is called the archetype instance pattern. Okay, it's a specific pattern, and it is one that you may decide that you want to use in your database design. Again, I will say that I prefer not to. Okay, as long as I can keep some sort of primary key in this case in the section, okay, that's the child, that keeps a level of uniqueness. Okay, when you have weak entities, okay, you just move that foreign key relationship down out of the primary key area into the regular attributes, but you still have a foreign key, okay, that points back to in this case, points back to the class. One of the things about that is this can be specified. The class name does not have to be a not null. Okay, you can specify that it is a nullable field. Okay, is this a good design? Again, it depends upon the business practices associated with this. If you have a section and you always want to know what the class name of that the section of the class goes with, well, it makes perfect sense that you should have that class name be a not null and a foreign key. So now we can mix together multiple types of strong, weak, many-to-many, one-to-one types of relationships, and all you're really doing in this case is you're following your data model and putting it together as a database design. And as you notice, really the only real difference is the specification of the primary keys and the foreign keys pointing backwards, and where do you place those foreign keys. So for example, in order line item, the item number pointing back to the item as a foreign key that is not part of the primary key of order line item. Perfect sense, correct? All right. And again, here is one that, and again, you will have, let's just say this, you will have multiple options associated that you can put together. So in the case of the employee skill, now you've got to make that the decision. Can a skill live all by itself with no employees actually having that specific skill? Well, guess what? I'm going to throw it out there again. It's a business decision. It's a business logic decision. But depending upon whether you decide yes or no, it will make an effect on how you do this. So in the case of the one on the right here, if you look at that table design on the right, where the name is is the name of the skill, a foreign key, which is not associated in the primary at all, and we don't know if that's nullable or not nullable, but the weak relationship says that that skill can live by itself, but the employee skill would probably need to have the name of the skill because it just doesn't make a lot of sense without it. But notice that you've also got this thing there called skill number, and that with the employee number becomes a composite primary key. Would I design anything this way? Probably would not use this design pattern. And we'll talk about later what design patterns would you use. Now, in the case of subtype relationships, another great specific situation. Remember, we talked way back when that you had this concept of employee, but there were different types of employees. So you had the ability to put all of that information into the employee table that was different between managers and DB admins. But if you make a relationship between the manager and the DB admin, and notice, manager and DB admin have as a primary key the employee number, which is a foreign key back to the employee number of employee. So a manager exists as a specific subtype of an employee, and a DB admin exists as a specific subtype of an employee. Okay. Now, can you have both a manager and a DB admin be the same person? okay, or have the same employee number? Well, in this case, unless you employ logic that says no, the answer is yes. Because the employee number being a primary key in both manager and DB admin, well, they have to be unique in the same table, but they don't have to be unique and related between the tables. Recursive relationships. This is always a fun one when you've got that foreign key to yourself. Okay, well, this is the good old linked list model, but bottom line is like in this boxcar relationship, you just say, you know, the boxcar ahead, and you point it back to the primary key of boxcar number. So boxcar number ahead has to be a boxcar. It's not the same boxcar. You don't put yourself in there. It allows that boxcar to point to another boxcar. Remember, it's a row pointing to another row. The representation of this as a recursive relationship is just a loop back to the same table. Okay, and there are other ways to do this. You can not just have you can have a one-to-one, but you can also have a one-to-many. Yes, you can. Okay. There are other ways to model this. We'll probably talk about that later as we get into more types of advanced designs, but realize that you have the way to represent recursive relationships in the one-to-one and also in the many-to-many and the one-to-many. Now, in the many-to-many, you do need to have a separate table to do it, to relate parts to part. Okay, and you're going to have a foreign key back to the part name. Okay, you're going to have a foreign key that points back to the primary key of part when you're doing this. So all of those situations are doable. One-to-one, one-to-many, many-to-many, recursive, non-recursive, weak, strong. There's a way to model them all. I've talked a lot about foreign keys and primary keys. Actually, it gets more, when you start designing these, it actually makes a lot more sense when you're actually doing it. Now, some of the more complex constraints, such as you must. Okay, most of the time I recommend to not use these types of constraints if you can find other ways to do it. But if you need the constraint to have, then you've got this. So, okay, must basically means must. This is a lot easier to do with an example. So the must not, and must cover basically means that you've got, in this case, if you have a must, that one exists, okay, it has to be combined with another to make the relationship. So let's look at this as far as a must. Okay, so we've got some salespeople, 10, 20, 30. And you've got customer table. Customer 1000 goes with 10, 2000 with 20, 3000 with 30. And this becomes a must constraint. So, in the third table, the customer number is 2000. Well, 2000 can only have the salesperson 20. So you must put 20 there. No other choice. Must not, well, it's exactly the same thing. If you have a must not, and this is a good drug and allergy, but we've got drugs and we've got customers and the allergy table 3000 and drug number 70 says it's an allergy. So therefore you should not give customer number 3070, or in the case here with the prescription, customer number 2000. If you go to 2000, you shouldn't give them 20 or you shouldn't give them 45. I think you can look and see the 20 and the 45 are ones that you shouldn't have for this customer 2000. That's a must not constraint. And must cover, again, same concept altogether. So in the case of repairs and tasks, so you've got to repair 20, and if you go over to 20, you see that 2002 needs to be covered for that specific task. You can just kind of look, there's 2001, 2001, 2001, 20, so you need a 2002. Okay, that's those. Now, I have personally never used the must cover in a database design ever. I have used the must and must nots, so, but I've never used the must cover. Doesn't mean that you may never see a situation to use it. It's just not one of the ones that you run into all the time. Now, cardinality. This is where you get a lot of fun that you have with this, but the relationships have basically 4 different cases. Parent and child are optional. Parents mandatory, child's optional. Parent optional, child mandatory. Ouch. Parent and child mandatory. Okay. And O to O, you don't need anything there. So here's the problem. Suppose you've got a parent. Suppose you've got in this case, let's say a section of a class with students in it, and you're going to delete the section. Now, the students are student enrollments. Well, if you delete the section of the class, you kind of need to delete the student enrollments. So what could you do? Well, one of the things is you could cascade the deletion. You delete the section, and all the enrollments go with it. Now, that's if the relationship has that requirement. You, in business logic, decide, is that requirement required? Same thing with an update. So updates and deletes are where you really need to make those changes and cascade them to the dependent pieces. Okay, so the parent's required, and you do an insert. Don't need to do anything. You just did that there. But in the case of the child, okay, you either put it on a parent or prohibit it. Again, these are going to make a lot more sense when you actually do them. Okay, but if you've got a child that has a required parent, that is your student and your section and student enrollment one, the logic should make sense. If you change the section or delete the section, you need to update all the students too. Now, the situation where the child is required, okay, this one's a little bit more complex, and I don't really have any good examples of this one that I can think of, at least off the top of my head. However, here's the thing. If you create a parent, something, let's say you create a section, but the logic is that you can't have a section unless there's students in it. Okay, well, you have to put one in there. Okay, that's it. I mean, that's the basics of it right there. If you delete the child and it's the last child, then the section goes with it. Okay, so in other words, if you have to have a student in the section for it to exist and you take it away, guess what? Yeah. So there are the one-to-many, the child-required actions, and the many-to-many. We typically don't, we try not to use those. And the reason is they're insanely difficult to force, and they're usually bad design. They're usually the result of bad design. I won't say they're bad, they're the result of bad design. When you run into those situations, you probably need to go back and look at the database design. However, sometimes you're contracted to come in and fix a database that was designed poorly. And when that case happens, guess what? You get the fun of doing it. Yes, but that's consulting. And when you have to fix those situations, it does pay pretty well. So we'll go with that. All right, the many to one. Okay, department is parent, employee is a child. Okay, now the department's the primary key, and the employees contain a foreign key that points back to the primary key. Okay, if you delete the department, do you delete the employees? Well, that would be the logic of a standard one. Now, the case of like the student and the section and the student enrollments, Well, I mean, if the section doesn't exist, there is no enrollment. But if the department doesn't exist, do the employees still exist? So then do you want to cascade all the deletes from that? If that's the relationship you would have with that parent-child, department employee relationship, and you get rid of the department, you got to delete the employees. Well, is that the best? Again, and this one I'm not going to answer because we're going to play with this a little bit more. But yes, this is a situation that you have to deal with. So if we were to set the foreign key to not null, then the employee can't exist without a department. Now, it could be redesignated, but now you got to throw in logic to redesignate. Well, can you? Sure, you can make a temporary department that would basically say unassigned is the name of the department. And then when you delete a department, all the employees that were part of that department go to unassigned, and it allows you to then assign them to other things. Or you could just simply delete the employees. But if you delete the employee, now you lose all the employee information, and the employee's probably still there. There are ways to deal with it, and I just gave you one of them. So now, this here says that these things require a trigger. I would definitely not use a trigger to deal with this situation. There are other ways to deal with it, and unfortunately, you're not going to learn those ways until you get to database 2. So right now, you're kind of stuck with triggers. There is a better way, okay? But this is the scenario, and you should understand it. We got a department. We got employees. We delete the department. Now the employees are their foreign keys are pointing at nothing, and we've got to do something with them because we can't let them point to nothing. Now, the other one, the O to M, you can insert new employees at any point in time, and there must be one employee for each department. Now, that might be acceptable logic. You can't have a department if there's no employee. As soon as you get rid of that last employee, you really need to get rid of the department because the department can't exist without an employee. Business logic. Okay. Now, so what do? You employ the logic that goes with the business logic. You say, okay, we get rid of the last employee, department goes too. Okay. Can't delete the employee if it's the last one in the department. You're going to have to do it some other way. Okay. In other words, if you put those constraint relationships in there and you try to delete the last employee, the database is not going to let you do it unless you employ some logic to not violate the constraints that you made. These are constraints. You're telling the database, don't let me do this. That's what constraints are. M to M, and they get a little bit more complex. But remember, in an M-to-M relationship, you actually have a relational table in the middle. So, what do we do in this case of an M-to-M? Well, one of the ways that you can do this is by employing triggers that say, don't let them delete this department without deleting the employee. Don't let them delete the employee without deleting the department. And then just figure out which one of those is going on and avoid the conflict. And we'll say there's a better way again. And again, you won't learn it until database 2. I will tell you what it is. You build a stored procedure that incorporates the business logic, and you execute it with the logic built in that you have programmed. And the reason this is better than a trigger is because triggers can have interesting and sometimes unforeseen consequences. I always stay away from triggers. So, can we do this? Documenting required parents, easily done. It's relatively simple. You just see it in the foreign key relationships. Do they have to exist? Is it null or not null? Okay, is it exist as a primary key, which is by definition cannot be nulled. Now, There's going to be questions. This gets much better. We're going to discuss this on the discussion boards. We're going to do some design work that actually was with tables. You're going to have a little bit of fun with this, but utilize common sense. Okay, I know you're dealing with terminology that is different, but the concepts are common sense. So that's it for this lecture, and this will get you going on database design, which is where it really kind of gets fun anyway. On out.